All right, so what do you think of when you hear the word force? Movement. Oh, I heard kinetic energy. Okay, push. All right, so we can exert forces on lots of things, right? Can each of you exert a force on something right where you are? Yeah. Yeah, like, oh, I heard it. What? Gravity. So are you all exerting a force right now? Yes. On what? On the chair. Now, oh, just a second. All right, so are you all exerting the same force on that chair right now?
No.
No, why not?
Better than the other.
Wow.
Or have more mass.
Yeah, I like that better. All right. Some of us have less mass. Some of us have more mass. Okay, so do you guys know what it is when you guys step on the scale in your bathroom? That isn't measuring mass, is it? I mean, it's not measuring mass. What is that measuring?
Your weight.
Your weight. Do you guys know what weight is?
It's the amount of force that's on your mass, isn't it? Kind of
What?
It's different for everybody because you have a different mass, and then part of the equation is your mass and the gravity.
Yes, and gravity. Now, we're all under the influence of gravity, which is a good thing, right? So gravity on Earth is the same for all of us. So weight is literally our force of mass times gravity. And if we have different masses, then our weight will be different. So you guys are all exerting forces right now. All right, so you guys are exerting a force on that chair. What's that chair doing to you? Pushing back. And it's what?
Equal or more. Equal.
Equal. All right. So that chair, because you didn't just fall through that chair just now, did you?
No.
Thank goodness. Okay. So you guys are pushing down on the chair, and the chair is pushing right back on you. You guys used to the equal but opposite reaction? All right. So we're going to talk just briefly about Newton's laws for forces. Does anybody know what the first law is? Oh, right, back here.
Okay, isn't it when an object's in motion stays in motion?
Yes.
Inertia.
All right. Yes, it has to do with inertia. I love it. All right. So when an object is in motion, it will stay in motion, and specifically, it will stay going in a straight path. Okay, at whatever speed it's going. It'll keep going like that unless what? An object in motion will stay in motion unless something acts on it. So specifically, on what acts on it? A force. All right. Now, what's the other part of that first law? So an object in motion will stay in motion unless something else exerts a force on it. An object at rest stays at rest unless something exerts a force on it. Good. All right. So how about the second law? This has to do with force? Yeah. Okay.
Something about reactance and
That's number 3.
Is it friction?
Huh?
Friction?
Not just friction. Oh, I heard acceleration.
Force times acceleration times speed. Force equals
mass.
So close. Force equals mass times acceleration. So F equals ma. All right, so what does this tell me though? All right, if I exert a force on you, for instance, she's sitting still, right? I come along and I exert a force on her, okay? I could cause her, if I gave her a big enough force, I could cause her to accelerate, couldn't I? Okay. Now, let's think about it. Let's put it all together. So, we have force equals mass times acceleration. So what does that mean? If I exert a harder force, what happens to the acceleration? It increases. It's going to move faster away, isn't it?
Yes.
All right, and then the third law you guys already told me about. So, is it all right if I push on you? All right. Hey, Ashley. So if I'm pushing on Ashley right now, what is her body doing to me? It's reacting, and she's pushing back with an equal but opposite force. some different types of energy?
Kinetic and potential.
Kinetic and potential energy. All right, you guys. Kinetic energy. What is kinetic energy? Moving energy. Yes. Okay, so kinetic energy is the energy that something has based on its motion. So the faster something's moving, the more kinetic energy it has. All right, what about potential energy? It is stored energy. I like it. Okay, so specifically, I'm going to be talking about, I'll just use myself. I'm going to be talking about gravitational potential energy. So, right now, I'm standing on this flat floor, okay? Right now, if I were to just step on something, I don't have much potential to do much. But if I go up a step, what happens? If I were to jump on something, I can put more force on it. So I have increased my what by increasing the height? I heard it. My potential energy. So think about this too, like with bowling balls. All right, you guys, so bowling balls. We've all felt how heavy those are. Have you guys ever dropped one on your toe? Oh my God, yes. Yeah, don't do it. All right, so let's talk about the gravitational potential energy of the bowling ball. All right, I don't have one with me. All right, but let's say that you have your bowling ball. I'm going to give you guys a choice. When we leave here, I have a couple of bowling balls out there. When we leave here, I'm going to let you all have a choice. You can either take that bowling ball, hold it right here and drop it on your toe, or you guys can lift it up and drop it from up here on your toe. So I want you guys to decide. Option A, and you know what? If you pick the correct option, I won't make you do this. Option A or option B? Who votes for A? Who votes for B? Interesting. All right, you guys, so those of you that picked A, why did you pick to drop it closer to your feet? Less force on my feet. Yeah. No, you're exactly right. It has less potential energy, and less energy means it's going to exert less force when it hits my foot. So those of you that picked option B, why? If I hold it up here, you guys,
Can you guys be respectful, please? Come on, guys.
I want you guys to be able to go on this awesome field trip and be able to think about physics at the same time. All right, so I hold it up here. What's going on with its potential energy? Has a lot more. So you guys, potential energy is more the further away it is from the ground. So if I hold it up here and I drop it, the force that it finally exerts on my toes is going to be a lot worse. All right. Then we also have other energies that I'm not going to really go into today. But let's start talking about some rides. Now, so when we talk about the rides, I want to analyze the physics of it. So are you guys all used to the Freefall rides? All right, so let's talk about how these rides operate. We start at the bottom, right? And then what do? They rise up, right? You can hear yep, you can hear it working. Okay, you're going up. So it is exerting, the machine, the engine is having to provide energy to raise you up. Now we all know, how exciting would this ride be if they only took us up this high and then let us drop? I would think that would be pretty exciting, but no, they've decided no. What are they trying to increase by making the tower tall? Potential energy. Now you're exactly right. So let's talk about this. They take it really, really up high, and then what do they do to you? They drop you. But they make you sit there for just a second, don't they? So they make you sit up there really high for just that momentary second to think you really made a bad choice getting on this ride. But you're all the way up here. Now, when it's still, Do you have any kinetic energy before you start to move? No, because kinetic energy you only have when something's moving. So up here, it's all potential energy. When it drops you, what's going to happen to your potential energy as you get closer and closer to the ground? It's going to reduce, because potential energy goes down when you get closer to the ground. Now, do you guys know that energy is always conserved, right? It's always conserved. It just changes forms. So if it's dropping and the potential energy is going down, what other energy is quickly going up? Kinetic. So where are you traveling the fastest in this ride? Toward the top or toward the bottom? Toward the bottom. All right, so you're dropping faster and faster and faster. And this is called free fall. At what is your acceleration when it just lets you fall?
Wouldn't it be 9.8 meters?
Yeah, what is 9.8 meters? Gravity. So they are literally, the only work that they have to do in order to get this ride to work is in the beginning where they raise you up and then they just let it go, essentially, right? And let gravity take over and everybody falls in free fall. All right? So, and that's all about transferring from potential energy to kinetic. So the higher those horrible things are, the better they are for you guys. All right, bumper cars. All right, these people are apparently having a good time. All right, so bumper cars. Now, let's picture that you're just sitting there. I've got some really awesome demos here. Don't be blown away by my plastic cars here. All right, so bumper cars. Let's say that you were unfortunate and you got the one bumper car that doesn't move. You guys ever done that before? Like, it's just awful, right? And you're just stuck there. But, do you just get to sit there at that same spot on the floor the whole time? No. No, what happens to you? Other people are hitting you. All right, so let's talk about the physics. This guy comes along and he hits me. What does he do? He exerts a what on my car? Force. A force. Now, what does my car exert on his car? A force, all right? So this is Newton's third law, right? He exerts a force on my car, and guess what? My car exerts a force back the other direction. So now my car is going to do what? Is it just going to stay there? No. It's going to move. Now, is this guy going to be able to go as fast as he was before he hit me? No, he slows down. So talk about energy. Which car gave up some energy and which car gained some energy?
Your car got
My car that was sitting still, it gained energy. What kind of energy? Kinetic. All right, this car lost some energy, didn't it? All right, how are we all doing?
Good.
All right, we doing good with all of Newton's laws?
Yeah.
All right. So what else can we talk about with bumper cars?
There's no seatbelts. It's barely seatbelts.
Are there not seatbelts? Well, that guy, all right, I think that there's a seatbelt, but that guy's breaking the rules.
They have the seatbelts because they don't want to climb out of the car.
Yes. Oh, that's a great point. He brings up a great point, you guys. If you are sitting in a car, or even in your, these don't go very fast, right? But when you guys are driving your cars, hopefully you always wear your seatbelt, okay? Because if your car hits like something else, right? Your car was traveling at, say, 70 miles per hour. When it hits, what speed are you still traveling? You as a passenger, 70 miles per hour. So if you're not wearing your seatbelt, that's why you continue to go forward. And you fly through the windshield and bad stuff happens. Now, I'm guessing this guy's breaking the rules because he figures he's not going that fast. But yes, at Elitch's, please wear your seatbelt. You know what? Are there, okay, I'll be honest. Who's been to Elitch's recently?
I went this summer.
All right, so I have not been in a really long time. I actually went there when it was still Elitch Gardens, so we won't. Yeah, if you don't know what I'm talking about, just It was better back then. But anyway, did they have bumper cars? How would you not have bumper cars?
I haven't seen them.
They have them at the fair.
They have